everyone. So today we're going to start talking about the physical properties of light. So we're switching gears a little bit from where we were with reactions and enthalpy of reaction, and we're going to talk about a different type of energy, and then from here we're going to build up to electronic structure, atomic structure, and molecular structure. So I'm really excited about this last section of the course. It flows very nicely, and I think we're going to have a lot of fun with it. So today we're going to start with physical properties of light. And our goal for today is to describe the observations that led to the model of wave-particle duality, particularly of light, and then be able to explain a little bit about what that wave-particle duality means. Okay, so let's start out just thinking about a source of white light and what happens if we take that white light and we pass it through a prism. So I'm going to do some illustrations. Always fun, not always clear. But I'm going to start with my favorite source of white light, which is the sun. Okay. So we have white light from the sun travels through space to the Earth. Okay. And then we're going to take that light and pass it through an optical prism. Okay. So what do you expect to happen when that white light passes through the prism? And this is something that you may have seen before in a different context or a different class. So what we expect to see is we expect that white light to be separated into individual colors of the rainbow. So we're going to have red light. Okay. So I have orange. We'll have yellow light. And then we have a green. We'll have blue. And then indigo, which is like a really dark bluish purple. So I use this usually for indigo. And then violet, which we usually see depicted as being a bit brighter. So here's our Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Okay. So Isaac Newton noticed this and way back in the 1700s. And so what Isaac Newton did was he looked at this phenomenon. And he said that white light is a continuous spectrum of all of the other individual colors. Excuse me, spectrum. There we have our prism. And so what a continuous spectrum means is that we don't just have red and then orange and then yellow. If you look in between, like on the rainbow that's cast, you'll see a continuous blend or an even blend of shades to go between orange and yellow, between yellow and green. So he said this would be a continuous spectrum. Okay, so go ahead and highlight continuous because we will come back to that. Okay. And so as physicists started to revise their understanding of light, So as physicists started to revise their understanding of light, we started to understand that light is a form of electromagnetic radiation. So light is energy that is being propagated by orthogonal, oscillating, electric and magnetic fields. So we can take or imagine an electric field. So this would be a single ray of light, one wavelength that moves forward. So here we're moving from left to right, and then the whole wave is going up and down. And then we can color this in. So we have our electric wave moving forward. Looks a little messy, so I'm going to erase that actually. And then if we imagine going from being straight up and down and then tilt to a right angle. So I want to tilt so that now I'm kind of going like in and out of the plane of the page. Okay. Then perpendicular to this light that we can see, there's also a magnetic wave or a magnetic field that has the same overall profile, but is tilted at 90 degrees. So this is our magnetic field. Okay. And this is going in and out of the plane of the paper. Okay. And so every time that you see a wave or you see light, there is always this perpendicular or orthogonal magnetic field. Most of the time we don't take that into consideration when we're looking at light or how light interacts with matter, but we do want to know that it's there, and it's really important because that magnetic field or putting light into a magnetic field can affect the way that the light moves and the way the light bends. So that's something that you'll see come up particularly later on in chemistry classes. Okay. So we know that light is this wave of electromagnetic radiation, and so we can characterize these waves by both their wavelength and their frequency. So I'm going to go ahead and draw another wave here. This is always the part of the quarter where I start looking around to see if I can find like a sine wave stencil. I've never quite found one, but I'm doing the best that I can here. So just kind of bear with me as much as possible. Okay, so here's a wave. So this would be a sinusoidal wave. It could be described as a sine or cosine function if you've taken math recently. And so we can describe this wave in terms of two factors, the wavelength and the frequency. Okay. So for the wavelength, we're going to pick a point on the wave. I'm going to pick the highest point. So this is the peak. Okay. And then the wavelength is going to be the distance between the equivalent point on that next period. So here, this is going to be the wavelength. And then we abbreviate this with the Greek letter lambda. So this is one of the lowercase Greek letters. Okay. And so I just happened to pick the peak here. You could also pick the lowest point in the wave. So this is called the trough. And if you go from the bottom of one trough to another, you'll have the same wavelength. So this will be the same lambda. You could also go, so if you imagine kind of like halfway through the peak and the trough, you could also go from where the wave crosses on one side through a full period to where it would cross on the other side, and then this will also be that wavelength. Okay. And just another thing to note here is that if you do bisect the wave, it'll be an equal distance between the peak and the trough. Okay. And then the frequency of the wave is going to be the number of waves that passes through a given point per unit time. So remember, we're looking at light waves here, and so light waves are being propagated, which means that they're moving forward. If you think about the light that comes from the sun, that electromagnetic radiation originates at the sun, but then it has to travel through space to get to us. Okay. So we have our sun, white light source. Okay. And then I'm just going to pick one kind of color of light. So if we think about our blue light moving forward from the sun. Okay. So here the wave is always moving, and what I have drawn is the forward or left to right direction. Okay. So I can pick a point in space. And then I want to see how many of those peaks pass through that space per unit time. So for each of these, for wavelength and frequency, we have standard units that we use to describe them. So for wavelength, that's going to be meters. Okay. So it's unit of length. We use meters. Okay. And then frequency, we're looking at the number of things that pass through per second. So that's going to be in inverse seconds, also called s to the minus 1, or this is called a hertz, and it's abbreviated Hz. So this is going to be per second, so that's 1 over s, and that's exactly the same thing as writing s to the minus 1. So anytime you see something to the minus 1, that means you can put it in the denominator and get rid of the exponent. Okay. And this is our hertz. Okay. So meters and hertz are the base units that we use, but you can also use millimeters, nanometers. You can use millihertz, although it's not as common. It's more common to change the units on meters, or the units of length, to a derivative of meters. Okay. So we have meters, we have per second. So we can use those two parameters to determine the speed that a wave is traveling. So the speed of a light wave, which is always abbreviated c, can be determined by multiplying the wavelength by the frequency. So if we take lambda times nu, that's equal to c. We can go through and check with our units to make sure that this makes sense. So for units, we have meters and then times s minus 1. That might look a little bit strange. We can also write this as meters times 1 over second. And then if you don't like the dots, you can use parentheses. So that is meters per second, and these are the same units as velocity or speed. So you can use this general formula for a sound wave, a water wave, really any type of wave, as long as you know the the wavelength and frequency. We're primarily talking about light. So the speed of light in a vacuum is actually a constant. So in a vacuum, the speed of light is 2.998 times 10 to the 8th meters per second. You'll sometimes see this in some textbooks as 3.0 times 10 to the 8th meters per second. Please don't use this value. It just limits your sig figs and limits the precision of your calculation. Okay. So always use that 2.998 times 10 to the 8th meters per second. So you'll notice that this is specifically the velocity of electromagnetic radiation in a vacuum. So when light is passing through a medium, so if it's passing through, say, air or a glass of water, it does slow down a little bit. But the amount that it slows down is going to be very, very small compared to the actual speed of light. So for any calculations that we're doing in this class, you can ignore any reduction in this speed. So any differences due to light passing through a medium, just for example, air. So just for example, air. So always use 2.998 times 10 to the 8th meters per second. Don't worry about if it's like in air or going through a gas. We'll just use that 2.998 times 10 to the 8th meters per second. Okay. So wavelength and in frequency. I should also explain the symbol that we use for frequency is nu. So nu is another Greek letter. Okay. And it's just pronounced nu, kind of like just N-E-W, but it's spelled N-U. This is another lowercase Greek letter. It looks a bit like a V, but it's kind of curved and looks a little bit italicized. So depending on the font, you'll see a little bit different. So here it's just kind of like a curvy V. I usually omit that leading tail and just do kind of like a V that's stretching over. So it's like bending over with one arm. Okay. Just beware of seeing like nu versus a lowercase v, because v can be used for velocity. So just be careful. Take a close look at the context to give you some clues as to which variable or which letter you might be looking at. Okay. So we talked a little bit about how we have our highest point of the wave and the lowest point of the wave. The distance between the highest and lowest point is called the amplitude. And that's abbreviated just with a capital A, so it's much more straightforward than lambda and nu. Okay. So we don't use amplitude in terms of calculating the speed, or you'll see the energy of light. What we do use it for, or what it corresponds to, is the volume or brightness. So we have this vertical distance between peak and trough. Which is our amplitude. And so for something like a sound wave, that's going to correspond to volume. So the bigger that amplitude is, the louder something is. And then for light, the amplitude corresponds to brightness. So if you have a really bright source of green light, that means that we have the same wavelength, we have the same frequency, the same speed, but that amplitude is bigger. So we're growing the height of our wave. Okay. And then the electromagnetic spectrum spans from gamma radiation, which is going to be very short wavelength, to radio waves, which are long wavelength. So we have this really large spectrum in terms of wavelength. So this figure shows you going from increasing wavelength. So we're starting at very short wavelength, so less than 10 to the minus 2. This is actually in nanometers instead of meters. So note the units here. And then we're going through the hundreds of nanometers, which is the visible range, up to 10 to the 12th nanometers, which is going to be like tens or hundreds of meters. Okay. And so another thing that you'll notice from this graph is that we have wavelength increasing on top, going from left to right. And then on the bottom, our frequency, if we go from left to right, is decreasing. So going from right to left is our increasing frequency. So wavelength and frequency are inversely related. So as the wavelength is increasing, the speed of light stays the same. So the frequency has to decrease. So as lambda increases, c, which is our speed of light, is constant. So that means that nu decreases. Okay, so let's start in the middle with this. So let's start with our visible light. So visible light is of particular interest to us because it's how we see different colors. And it's something that we can sense very readily with our eyes. So the visible region of light goes from 400 nanometers, give or take, to 750 nanometers. And then we go through the full rainbow. So this is in a kind of reverse order of how I drew the rainbow before. So we have our violet light is very short wavelength, or relatively short, so on the visible light spectrum. And then we have a higher frequency. And then we go through our indigo, our blue, green, yellow, orange, and then this large red region. So red light is going to be longer wavelength and then a lower frequency. Okay. And then it looks like the unit here got cut off a little bit. So it's s to the minus 1 for that, for the hertz. Okay. So then we have ultraviolet light, we have our X-rays, and then gamma rays. So these are all shorter than violet light. And then if we go past red to longer wavelengths, we have infrared, we have our microwaves, and then we have our radio waves. So I want to write these out in a slightly different way. Okay, so I'm going to start with my let me write this. Okay, so if we go from gamma rays to X-rays are ultraviolet rays. Then, so ultraviolet is kind of like beyond violet. We have our visible, our infrared. So that's going past the red that we can see visibly. And then we have our microwaves and our radio waves. Okay. Then I'm going to pull this and just center it a little bit. Okay. So visible light is a light that we can see. So we can sense this with our eyes. Okay. And the human eye just happens to detect light from about 400 nanometers to 750 nanometers. As you get a little older, you start losing some of those, some of the shorter wavelength cones. So this is a very kind of like human-centric visible region. There is some evidence that other types of animals have evolved to sense different regions of light visibly. So our visible region isn't necessarily the same as every animal's on Earth. Okay. We can also sense infrared radiation. So infrared radiation is heat. So if you think about heats of reaction or an exothermic reaction or an endothermic reaction, that heat that's given off or absorbed is a form of electromagnetic radiation. So the electromagnetic radiation is interacting with matter on some level. Okay. I just think it's kind of cool that the light that we can see and then the heat that we feel are actually the same thing. We just sense them differently. Okay. Microwaves you're probably familiar with. We do use these to cook food. Okay. So if you have a microwave at home, you've probably used those. We definitely have one. We have a few on campus you've probably used. Microwaves are also used for medical imaging. MRIs or magnetic resonance imaging are based off microwaves. And radio waves. And then radio waves are these really long waves. They have wavelengths that are meters long, and they're just all around us. So every radio station is emitting these radio waves. And so we can use those for information transfer. Okay. And then as we go to our shorter wavelengths, ultraviolet, this comes from the sun. This is actually the type of radiation that causes sunburns. Or any other type of sun damage. Okay, and then X-rays are even shorter. X-rays will penetrate soft tissue, and so we can use these again for medical imaging. Okay. And then gamma rays are the shortest wavelength of electromagnetic radiation that we've characterized. There is some amount of gamma radiation that's emitted from the sun. It's also involved in radioactivity. So a lot of the compounds that Marie and Pierre Curie worked with gave off gamma rays as a form of radiation. Okay. So here in this list our wavelength is increasing, going down. And then the frequency is increasing, going up. Okay. The other thing that's changing here is the energy. So gamma rays have a higher energy than radio waves. So as the frequency increases, the energy also increases. So anytime you have short wavelength, it's going to be high frequency, high energy. It also tends to be the most damaging. So when we have our short wavelengths, there'll be high frequency, high energy, and will also cause damage to tissues and DNA. And radio waves really don't cause any damage at all. They're like all over the place. They just don't penetrate at all or cause any type of damage. Okay, so let's go through an example. I'm not going to do every part of this in the interest of time. I just want to show you how we can use this equation or the speed of light to get some additional information. So a dental hygienist uses X-rays, which have a wavelength of 0.50 angstroms, to take a series of dental radiographs while a patient listens to a radio station. So here we're at 325 centimeters, so that's about 3.25 meters, and looks out the window at the blue sky, and the wavelength of that blue light is 473 nanometers. So we want to calculate or be able to calculate the frequency of the electromagnetic radiation from each source. And we want to assume that the radiation is traveling at the speed of light, 2.998 times 10 to the 8th meters per second. So here it is very explicit. Okay. But this is a general assumption unless stated otherwise. Okay, so I'm going to use the equation. I'm going to do this just for the X-rays. We're going to use C is equal to lambda times nu. And then I want to rearrange this equation to solve for the frequency. So I'm going to divide through by lambda to get nu by itself. And so then we get C over lambda is equal to nu. So now this is basically a plug and chug, but I will also want to put in some conversion factors. Okay. So I'm going to switch to writing over to the right side. Excuse me, I feel a sneeze coming on. Okay, so we have 2.998 times 10 to the 8th meters per second. And then divided by the wavelength, which we're given is 0.50 angstroms. So we want to make sure that our units match. We want to end up with per second. So this is good. But our meters and angstroms don't match. So you might remember angstrom from a couple of weeks ago. So 1 angstrom is equal to 10 to the minus 10th meters. So this is not a standard it's not a standard SI abbreviation or a standard SI prefix, but it is a particular definition that we'll come back to again and again in chemistry. And the reason for that is that the angstrom is on about the atomic scale, so it's a convenient unit to use. Okay, so now I want to put my conversion factor into the denominator. So this is going to get kind of long. Okay. We have 10 to the minus 10 meters per angstrom. And now I want to check how my units cancel. Okay. So I have, in my denominator, I have angstroms divided by angstroms. So that will cancel. And then I have meters in my numerator. And then that will cancel with the meters in my denominator. So then I'll be left with the per second. And then if it kind of confuses you to have multiple numerators and denominators in your fractions, instead of writing this as m/s, you can go ahead and write this as meters times second to the minus 1. So then you can really see that that s to the minus 1, or that units of hertz, is going to come out on top as our primary unit. Okay, so now we want to go ahead and, yes, this is plug and chug. So I'll plug this in my calculator. 2.998 times 10 to the 8th, and then divided by 0.5 times 10 to the minus 10. And then this is coming out to 5.996 times 10 to the 18 per second. So let's go back and check on our scale to see if this is reasonable. Okay. Okay, so here we're at the visible. So we have an X-ray. So we're down at the order of kind of 10 to the 0, 10 to the minus 1 nanometers. And then we're right there at 10 to the 18 per second. So this is definitely a reasonable answer to get. And then I know that we always want to go back and check our significant figures. So our significant figures are not being limited by our conversion factor. So that's, or by our speed of light. They're never being limited by our conversion factor because that's going to be an exact ratio. The speed of light is not going to limit our precision because here we have 4 significant figures. And that's always a good practice. You really never want a fundamental constant or a constant you're using to limit the precision of your calculation. So we're really only limited by our wavelength, which has 2 sig figs. So our leading 0 is not significant, the 5 is significant, and then our trailing 0 is significant. So I can round this to 2 sig figs. So I have 1, 2, and we have a 9 here. So then we're going to round up. So then this is approximately equal to 6.0 times 10 to the 18 per second. Okay. And then I would encourage you to go back and do the radio waves and the visible light waves on your own, just so you get some practice with these calculations. Okay. So next, let's think about some interactions between waves. So we'll just start out thinking about water waves. So if you take water, or you see like a pond or pool of water, okay. And then if you drop a pebble, or throw a rock in the water, what's going to happen? So what you should see is you'll see ripples that start to form and go out from the point where the pebble was dropped. So we're going to take a pebble and then just plop it in. Okay. So you'll see waves that move outwards. And so usually what those look like are ripples on the surface. Okay. And then what would happen if we take a second pebble and plop that in nearby? Well, you'll get a second set of ripples. Okay. So there's going to be points where these ripples or waves cross over. And so we want to think about what happens at the points of crossing. Okay. So there's 2 options. You could have in phase or out of phase interaction. So if the 2 waves or ripples interact completely in phase, that means you have 2 identical waves. So we're going to have 2 waves with exactly the same wavelength and the same frequency, moving at the same speed. So here we'd have an in-phase interaction. What happens with these 2 waves is that they're going to add together and make one with double the amplitude. So the wavelength doesn't change, the frequency doesn't change, the amplitudes add, and then we'll get one wave with twice the amplitude. So if on our first wave we have just A, then after we have the constructive interference, then the amplitude is going to be 2A. Okay. If we have out of phase interaction, then that means that our 2 waves, instead of being right on top of each other, are going to be offset by exactly half a period. So whereas before, so it's like now you can see where we have a peak, the second wave has a trough, and where the first wave has a trough, the second wave has a peak. Okay, so I'm going to pull this. Let's see, I'll leave it here, but I want to recolor it just so that you can see the difference a bit better. Okay, so that's not too dramatic. Get a brighter color. Okay, so now we have our 2 waves interacting completely out of phase. Then the same thing's going to happen where our amplitudes are going to add, but now we have one where we have a positive A, and then it's going like negative A in the opposite direction. So when two waves that are completely out of phase add together, we just get a flat line. So those two waves cancel. Okay. And so you can think of it pictorially, mathematically. We'd have like A plus A, so those two amplitudes add, and then we get 2A. With our out of phase interaction, mathematically we'd have our positive amplitude plus our negative amplitude are going down, and so that just equals 0. Okay. So we can use the same principles with light or interactions between light waves to make what's called coherent light. Okay. So coherent light is a particular type of light or radiation that's all in phase and is typically generated using a laser. So laser is in all caps here because it is actually an acronym. It stands for light amplification through stimulated emission of radiation. Okay. A really popular type of laser, at least in the science world or in the physical sciences, is a neodymium YAG laser. So an ND YAG, and this is a type of really bright green laser. They're really powerful. They can cause a lot of damage to your eyes, so you have to wear special goggles if you're in the room with one. So a neodymium YAG laser is going to pulse light. So you have this stimulated emission or stimulated formation of light. Okay. Okay. And so it's really bright green. So we have kind of a shorter wavelength light, medium visible. Okay. And then we'll have many, many copies of the same wave. And so these are all going to be in phase. They're all going to line up perfectly together. So all of our peaks are lining up, all of our troughs line up, all of the individual wave periods. Okay. And we can keep going here. So what this ends up forming, or how we represent this, or we typically show that we have our peaks we usually show as kind of like a bright line. And then the troughs we would show as kind of no line. So the way that we represent coherent light pictorially is by successive thick vertical lines. So here is my artist's representation, or kind of overlay of how we would show this. Okay, and then a little bit there. Okay, so what happens if we take this coherent light and we pass it through a wall with a hole in it? So this is called the double slit experiment. Okay. So in this case, we're imagining taking our blue waves, where all of those waves are in phase. So here, those in phase waves are being indicated by these alternating lines. But really what's happening is we have all of those waves on top of each other. So I'm going to, so if you draw kind of over it, you'd have a peak, a trough, peak, trough, peak, going all the way down. So that's where our coherent light is coming from. And then we're going to shine this light onto a wall or a piece of paper that has two holes cut in it. So these are our double slits. Okay. And so what happens when the light or all those waves of light pass through the slits is that they bend. They don't just pass straight through. And so here now we have our light is moving off in kind of bending to different degrees. And so what we have are we have multiple regions where the waves are overlapping. And so what we're going to end up with is alternating in phase and out of phase interference. So the waves bend. Okay. And then we get interference. And then if we kind of hold up another piece of paper, another wall, we can look at the patterns that are formed. And we'll see that there are regions of light and dark. So we'll have bright regions where all of the waves are in phase. We have like a really bright spot. Then we'll have some where there isn't quite perfect in phase overlap. And then we'll also have regions that are completely dark from the waves being out of phase. So here, this figure is showing the same thing that I showed before. We have our in phase makes a big wave, and then our out of phase, we have just a line. Okay. So, and then we can see the same type of constructive or destructive pattern happens if you drop two pebbles into water. You still have the waves going out. You'll have some regions where it gets really flat, and then some regions where it gets really high. If you've ever been in like in a boat on a lake, and then like sometimes the motorboats will go by and they create a lot of wake. If you get hit with wake from two boats at the same time, like you'll have this like really bouncy kind of experience. And that's because those two waves can add together and increase the amplitude of oscillation. Okay. So this property where waves bend when they pass through a slit is not unique to light, but it is unique to waves. So these diffraction patterns are completely unique to anything that travels as a wave. In contrast, particles do not diffract. So if I take like a bunch of ping pong balls, and I throw them at a wall that has two holes in it, then it'll either hit the wall and bounce back at me, or it'll go through and it'll just go straight through. So the ping pong balls are going to go through and then bend off to the side, and they'll bend down a little bit because of gravity, but they will just like kind of go through. They're not going to bend, they're not going to bend up, for example, the way the waves do. They'll only bend down. Okay, so why do some objects emit light? Why do some objects emit light? So why does the sun, my favorite white light source, emit light? What about an electric stove? So you might have an electric stove with a metal coil, and those metal coils will get they'll get kind of like an orange, like dark red color when they get really, really hot. What about light bulbs? So why do these particular objects emit light? So these objects are a particular type of radiator. So radiator means that they emit electromagnetic radiation. And they're called black body radiators. And so a black body radiator is an object that emits visible light specifically due to its temperature. So it's an intrinsic source of light. So it's not like a leaf where you have to shine light on it and then the green light is reflected back to you. This is intrinsic to the object. And then the color of the object is going to depend on how hot the black body radiator is. So an electric stovetop gets up to about 1,000 Kelvin. So that would be red hot. So if something is red hot, it's going to be about 1,000 or 1,000 plus Kelvin. So there's an actual temperature that we can associate each of these colors with. White hot is, looks like about like 6,500, maybe 7,000 Kelvin. Once we get, our sun is around 5,000 Kelvin. So it's kind of like the yellow-white region. If we get even hotter, then that's where we start seeing blue light is emitted. So at higher temperatures, black body radiators will emit more short wavelength light. So this is just the color that we see here. It's actually emitting a full range of wavelengths. Okay, so here, so higher temperatures, black body radiators will emit more short wavelength light. So this is from a physics website, and I found this figure really helpful. It's got a lot of information on it, so I'll take you through it kind of slowly. So the first thing we always want to do anytime we're looking at a graph is see what our axes are. So our x-axis is wavelength, and this is in nanometers. We're going from 100 nanometers, which would be the short UV range, up through thousands of nanometers, so into the infrared. And then our y-axis is something called power density. And then this is 10 to the 13, so this would be 1 times 10 to the 13, 2 times 10 to the 13, 3 times 10 to the 13. That's what that information means. And then it's in watts per meter cubed. So we're kind of normalizing the amount of power to the volume, or taking the density. This would be... this isn't a set of units that we'll use very much or really at all in this class. So this would be more similar to the intensity or brightness. So what this is telling us is that for different temperatures, what wavelengths of light are being emitted the most or the strongest. So we have our, so we have different lines here. So the solid line is at 6,000 Kelvin. The long dashed line is at 5,000 Kelvin. So this is similar to the sun, okay, or our sun. And then we also have 4,000 Kelvin in the short dashes, and then 3,000 Kelvin in the dots. Okay, so what we want to do is look at how these peaks or how these profiles change at higher temperatures. So at 3,000 Kelvin, the peak is going to be at about 966 nanometers, which is in the IR. So this isn't necessarily going to be, so this will be very warm. And then we also have a little bit of emission in the visible range. So at 3,000, we're going to be seeing those red and orange wavelengths of light. But then most of the radiation that's being emitted is going to be in the infrared. So that's going to be sensed as heat to us. When we get up to 4,000, that's where we start getting, our peak now shifts over into to 724 nanometers. So definitely in the red. So our peak is shifting up because we have more energy. And then also shifting over to the left or to shorter wavelengths. Okay. 5,000 is the sun. So this looks mostly yellow to us just based on the combination of wavelengths. The peak is at 580. So the peak is at where the green light is. So plants have actually evolved to not to absorb the strongest wavelengths of light from the sun for the most part, because it would just be too much energy. Okay. And then at 6,000, our peak shifts up and to the right even more. Now our peak wavelength is at 483 nanometers, and then that's going to be more getting into the white. So the more mixture of wavelengths we have, so we have lots of violet and lots of red and all the wavelengths in between, that's when we start to see white, or things start to look white to us. Okay, so we can continue getting hotter, but the profile of the wave doesn't change. So you'll notice that all of these, after their peak, will drop back down to about 100 or so. So as we keep getting hotter, the profiles get bigger, they move over, but they always drop back down. So we don't have anything where we have that peak is going to be like permanently going up. So the profile always drops back down. It never just continues increasing. And then there's also an equation here. We're not going to use this, but it does allow you to relate the temperature to the wavelength. So if you want to measure the wavelength, or you want to determine the temperature of an object, you can use the wavelength of the peak. So this is actually used a lot in astronomy to determine the temperatures of distant stars. And I love those intersections with physics and chemistry and astronomy and how we can use this to gain information about the world around us. Okay, so we would expect as you move to higher and higher temperatures that you would just continue to emit more and more in the UV. So we have these shorter wavelengths, it's getting hotter. So why does, so basically the sun doesn't emit very much in the UV, which is really good for us because it would cause a lot of damage if it did. So this observation was really confusing to European physicists in the 1700s to early 1900s. And it took a while to for them to kind of understand or explain why this happened. So Max Planck is given credit for the explanation for why the UV doesn't just keep increasing with the sun. This is called the ultraviolet catastrophe, which is a great name for a band. Okay. So Max Planck called this an act of despair. He didn't like this theory, but he felt that it was the only thing that explained the natural world or could explain their observations at the time. So I did want to include this picture because here we have Max Planck at a dinner party with several other prominent physicists and chemists at the time. All 5 of these men won Nobel Prizes. So Nernst, studied electrochemistry and gave us the Nernst equation that you'll learn in 1C. Albert Einstein we'll talk about very soon. He's probably the most famous physicist of the 1900s. R.A. Millikan, who did the Millikan oil drop experiment and determined the mass-to-charge ratio of the electron. And then von Laue also won a Nobel Prize in physics. He studied X-ray diffraction, and so he gave us some of the technology that we use to determine molecular structure now. So one reason I wanted to include this was because I just want to show you that particularly in the 1900s, the Nobel Prize was very much kind of like a club. So all of these scientists worked together, they nominated each other for prizes, they were awarded prizes. So it was a very insular set. And I just think that given the prestige of the Nobel Prize, it's really important to acknowledge just how restricted it was to a certain group of people. And to a degree, continues to be. So I just encourage you to think about that, and then maybe what the possible ramifications of that are in terms of our scientific understanding of the world. Okay, so to avert what was termed the ultraviolet catastrophe, Max Planck reasoned or determined in the 1900s that a black body radiator could only emit certain packets or quanta of energy. So he said that the energy of a particular wavelength of light, so here it says E, we call this E light, okay, is equal to some positive integer n times h times nu. So n is just any integer, or any positive integer. Okay. And then nu is still our frequency. Okay. And then h is a factor called the Planck constant. So the Planck constant is equal to 6.6260689 times 10 to the minus 34 joules per second. So our energy is going to be in joules. And I just want to emphasize how small this really is. So if we look at heats of reaction, those tend to be in the hundreds or thousands or even tens of thousands of kilojoules of energy. And now we're down at 10 to the minus 34. So this is an incredibly small packet, but it does have really dramatic consequences for our understanding of light, and even our understanding of visible light. Okay. So whereas Newton said that visible light is a continuous spectrum, we now know that it's not. So if you use really high-powered prisms and you take that rainbow, you can see that it's not a perfect continuous spectrum. There are little gaps in between, or little pixels. So it's kind of like the difference between if you see a painting in real life versus a digitalized painting, where if you zoom in, you can see those little individual squares or individual pixels of color. So light in the real world is actually comprised of like little pixels. But the difference in energy between each of those pixels is 6.26 times 10 to the minus 34 joules. So it's a really, really small difference. It's so close to being continuous, but it's not. So we do have discrete and distinct colors in our rainbow. And that's true not just for visible light, but for the entire electromagnetic spectrum. Okay, so what this means is that matter or waves can change its energy by integer multiples of h nu. So the energy change between adjacent states, which we call delta E, is equal to Planck's constant times the frequency. Okay. And we can calculate this delta E the same way we've calculated other deltas or changes, where we have our E final minus E initial. If our initial state is n, then our E final for the adjacent state is going to be n plus 1. Then we'd have n plus 1 times h nu minus n h nu. And then we can factor out, or we can factor this through, so you get n h nu plus h nu minus n h nu, and then we get delta E is equal to h times nu. So remember, h is that 6.626 times 10 to the minus 34 joule seconds. Our nu is going to have units of per second, so the energy will always come out to joules, or J. If you've taken a lot of physics classes, you may have seen h bar. H bar is different. That's going to be h divided by 2 pi. So that's not equal to h. So if you're used to seeing equations with h bar, do not use the same equations with Planck's constant h. Those are different values. Okay. So if we think about energy, just any type of energy on a scale, it's not gonna behave like an elevator or a ramp. It's always going to be like a staircase. So in terms of just how energy, or the energy scale, we don't just kind of continually increase. We have individual allowed energies that can occur. And then the gap in between each of these states is Planck's constant times the frequency of that radiation. Okay. So if you have a really high, really large frequency, the gaps are going to get bigger. If you have a really long wavelength, low frequency, the gaps are going to get smaller. So here we'd have like a long lambda, and then for shorter wavelengths, those gaps get bigger. Okay. So energy is a staircase, not an elevator. And so this means that energy is quantized. So the little quanta are little packets. Overall, our energy is quantized. So we can be one energy level or another, but we can't be anywhere in between. Okay, so another really important piece of the puzzle here is something called the photoelectric effect. So I'm going to show you another video on a demonstration on the photoelectric effect, and then we'll come back and talk about it.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a Perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on, and it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
Okay, so what the demonstration in this video showed you, and I'll include a link to it online as well, is that if we take light of a certain energy, we can make electrons move. So if we take visible light and shine it onto a piece of metal, nothing happens. If we start taking higher wavelength or lower wavelength light, then we can see that that electrons will move, or we can charge or discharge a piece of metal. Okay, so here's a figure that shows this from the OpenStax textbook. So here we have a single piece of metal, and this is a little bit different in that here we have only visible wavelengths of light, but the overall principle is the same. The exact behavior will depend on the material being used. Okay, so if we take red light, shine it on this particular piece of metal, nothing happens. So there's no electron ejected. If we take green light at 550 nanometers, so maybe this is coming from a laser, and we shine it on the same piece of metal, now we can do is we can pop off an electron, and we can measure the velocity of that electron. Okay. And then here we have even higher energy light, so higher frequency. This will also pop off an electron, and then now we can measure the velocity, and it's going to be higher. So now we're at 6.22 times 10 to the 5th meters per second. Before we were at 2.96 times 10 to the 5th meters per second. So I want to make a graph of what this looks like for any given piece of metal. Okay. So here we're going to have the energy of light. Okay. So typically we put this in joules. So it's going to be the energy of the light that's hitting the piece of metal. And then on the y-axis, we're going to have the velocity of the electron. And this will usually be reported in meters per second. You'll notice the electrons are moving pretty fast, so on the order of 10 to the 5th meters per second. So we're not quite at the speed of light, but we're definitely getting close. Okay, so for our red light, we can take the brightest red light you have ever seen, shine it on this piece of metal, and nothing will happen. Like, absolutely nothing. No electrons ejected. It might get a little bit warm, but really, like, nothing else is going to happen. Okay. And then we're going to hit what's called a threshold frequency or threshold energy. And that's sometimes abbreviated as a big theta. So once we hit that threshold energy, so as we're getting to shorter wavelengths, higher frequencies of light, then we start to pop off electrons. And then as we increase the energy of light, the energy of that electron or kinetic energy also increases. Okay. So this is another phenomenon that was confusing to scientists because if we know that the energy of light is equal to Planck's constant times the frequency, it seemed reasonable to think that you could shine red light onto a piece of metal and that it would be able to kind of like keep absorbing the energy, and then eventually it would pop off an electron. But that's not what happened under any circumstances. That never happens. You need to reach a minimum frequency or threshold frequency in order to pop off the electron or to ionize and eject the electron. So what Albert Einstein actually won his Nobel Prize for was for explaining the photoelectric effect. So I know he's mostly famous now for relativity, but he didn't win the Nobel Prize for that. He won much earlier for the photoelectric effect. So he said that light is a particle. So I just went through all this evidence for why light is a wave, but now we're saying that light, maybe it's actually a particle that travels in quantized packets of energy called photons. These are sometimes called wave packets. And the photon now is a massless particle. So light behaves as a wave and as a particle and exhibits what's called wave-particle duality. So just in summary, light and electromagnetic radiation. So we say light, but that includes infrared radiation. It includes X-rays, ultraviolet rays, radio waves. Can always act as both a wave and a particle. This is called wave-particle duality. So it's not a wave or a particle, it's both. And the energy of electromagnetic radiation is quantized and comes in discrete energy packets. So that's the end of this particular video.